Hello, everyone. This is a video lecture for topic 6, momentum, impulse, and collisions. So what is momentum? Momentum P is a vector quantity that is a product of mass times the object's velocity V. The SI units for momentum are therefore kilograms times meters per second. And momentum is a vector quantity, so it has x and y components, where x component of momentum px is mass times velocity x component, and the y component is the mass times velocity y component. The kinetic energy is the momentum squared over 2 times mass. If you have multiple objects, we call a system momentum the vector sum of individual momenta of the parts of the system. So here's an example. We have 2 carts mounted on the air track moving towards one another. And the first cart has a speed 0.8 meters per second and a mass 0.38 kilograms. While cart 2, we are given the mass, but we're not given initial speed or velocity. Note that this is a one-dimensional problem. So the velocity can be either positive or negative. And we are free to choose which one is positive. Since they're moving towards each other, the other one will have to be negative. So let's try to answer the questions of this problem. It says, if the total momentum of the system is to be 0, what's the initial speed of cart 2? So we know that total momentum P is, because we have 2 parts of the system, is going to be mass of the cart 1, which is 0.38 kilograms, multiplied by its velocity. So I choose the velocity of cart 1 in one dimension to be positive 0.8. So we're just going to multiply by 0.8 meters per second. And then I have to add mass times velocity of the second cart. So we know that the mass of the second cart is 0.71 kilograms. And we don't know the velocity of the second cart. So we're given that the total momentum of the system needs to be 0. So we solve for V2. V2 will be negative 0.3 times 0.8. And then we divide that by 0.71, which is the mass of the second cart. Give me a second to calculate that. This will be about negative 0.4. Does it follow that the kinetic energy of the system is also 0 since the momentum of the system is 0? So the momentum of the system can be 0 because we're dealing with 2 vectors that point in opposite directions, so they cancel each other. However, the kinetic energy is the sum of the total kinetic energy of the system will be sum of the individual kinetic energy of each cart. So we need to do half of the mass of the first cart times the speed of the first cart squared plus half of the mass of the second cart times the speed that we find in the first part squared. So we found that it's going to be negative, let's say 0.4. I might be too rough. But you can see that even though the velocity is negative, we still square it, so the whole thing is positive. So then the whole thing is the sum of two kinetic energies is not zero. And then if you calculate it, this is going to be the answer for part 3. Okay, so back to where we started, the momentum is mass times velocity. It's a vector. In one dimension, it means it can be positive or negative. In 2 dimensions, it means it has x and y components. And if you have multiple parts in the system, then you just add their momenta as vectors, taking care of the coordinates and the signs. Now let's do think pair share 1. The question is if we have 2 masses, M1 and M2, and M1 is less than M2, so you have one mass that is smaller than the other, but we are given that they have equal kinetic energy. The question is, how do their magnitudes of their momenta compare? So in order to solve this, we need to remember that we just said that the kinetic energy of a single mass is half of the momentum squared over 2 times mass. So we can write, since both kinetic energies are equal, we can write that P1 squared over 2m1 equals P2 squared over 2m2. And we want to know how does P1 relate to P2? So for that, we'll manipulate this equation. We'll move P2 squared over to the other side. So that will give us P1 squared over P2 squared. And 2 times the mass, we will move to the right side. So we'll have 2 mass 1 over 2 times mass 2. And we know that mass 1 is less than mass 2, so this whole thing is less than 1. That means P1 is less than P2. So we choose answer number 2. This question tests our knowledge of kinetic energy written in terms of momentum. Okay, next, we will look into how momentum can change. As we recall from second Newton's law, the net force equals mass times acceleration, but now we will write acceleration by its definition as change in velocity over change in time. But that means that mass times change in velocity, which is change in momentum over change in time, equals our net force. So we can write that change in momentum over change in time equals the net force. This equation is also valid when the forces are not equal, and also not constant. And also, we need the time interval to be sufficiently small so that we can evaluate this as an instantaneous acceleration or instantaneous change in momentum. So we now know that change in momentum over change in time equals net force acting on the object. If we multiply both sides of this equation by change in time, we get force times change in time. We're going to call this quantity an impulse of force F acting on the object during time interval delta t. So we can say that what changes the momentum or change in momentum equals impulse done by force F within period of time delta t, where change in momentum is mass times final velocity written as a vector minus mass times initial velocity. We call this equation impulse momentum theorem. and we're going to use it to solve certain problems. What we need to take out of this theorem is that once a force has acted on an object, it will change the momentum, and we're going to call that change in momentum an impulse. If the force is not constant with respect to time, so here's an example in the graph where the force is increasing with time and then decreasing. So between time interval t initial and t final, we have this time dependent of the force. In that case, the impulse equals the area under the force versus time graph. But in order to simplify our calculations, we usually define an average force as an effective force that delivers the same amount of impulse to an object, which means the area under the average force graph is roughly equal to the area under the curved graph. So let's consider some examples where the impulse is used or we're asking to calculate. In this problem, a 0.18 kilogram volleyball approaches a player at the speed of 15 meters per second. The player then strikes the ball with her fist and causes the ball to move in the opposite direction with a speed of 22 meters per second. So again, this is a one-dimensional problem because we're not told about X or Y directions, and the speed is not specified whether it's to the left or to the right. We just know that after the strike, the speed changes to opposite of what it's been before. So to write down the impulse, we will just follow the definition of impulse. That impulse is a force times delta t. And it's also equal to P final minus P initial, written as vectors. So in the problem, we're going to read the problem again and realize that we're not given force or time, but we're given V initial and V final. I'm going to go ahead and choose that the speed after the collision is positive. That means that the speed before the velocity before the strike was negative. Does it make sense? They just need to differ by a sign. So in order to write down final momentum, I will use the mass. That 0.28 kilograms is our mass. And then I'm going to multiply that by the final velocity, which is 22. And then I have to subtract, again, mass times the initial velocity. So 0.18. But here I need to be careful. So if 22 was positive, then the 15 has to be negative. So I have to multiply my mass with the negative 15. Why is it important? It's because we are subtracting the initial value, and it's by itself, it's negative. So when we're subtracting them, it's going to turn into a sum. So we have 0.28 times 22 minus negative 0.28 times 15. So it's going to be adding those two together, and we're going to have 0.28 times 37 as a result. And you guys can calculate that, whatever this is equal to. So let's just assume that it's going to be about 13, okay? What are the units of impulse? They're the same as the units of momentum. So it's going to be kilograms times meters per second. Okay, let's say this is our calculated result for impulse. Then next question says, if the player is in contact with the ball for 0.06 seconds, so what is this value? It's our delta t. So now we can say impulse equals to force times delta t. And which force? They're asking us to find the magnitude of the average force. So that means 13 that we found in the previous part equals what we need to find average force times 0.06. And we solve that for the average force. Okay, so these are the examples of how we use impulse. Impulse can be on one hand, it is equal to final momentum minus initial momentum. On the other hand, it's equal force times the time interval. If the problem gives one or another, then we can solve using these equations. Here's another example where we're gonna use impulse as an area under the force graph. We're given that the mass is 1.4 kilograms, and the force is given as a variable force that changes with time. Between 0 and 2 seconds, it's linearly increasing, and then it stays constant for a second, and after that, for between 2 and 3 seconds, it stays constant, and after that, it linearly drops back to 0. So given this graph and the mass, we need to find impulse of this force and the velocity of the particle if it was initially at rest. So the impulse equals area under the graph. And how do we estimate the area? We can count the boxes or just use break this shape into more easier shapes to deal with. So we know that area of the triangle is half base times height, and the area of the a bar, a rectangular bar, is base times height, and then we have another triangle. So we're gonna do 1/2 times 2 times 8 plus the base is 1 second and the height is 8 newtons. And then we add again 1/2 of 2 times 8. That's gonna give us 24. And what are the units of the impulse? Again, it can be either newtons per times seconds, or it's the same things as kilograms times meters over second. So this is our impulse of this force. So to find the final velocity, we recall that P final minus P initial is impulse, which we just found, which is 24. But what is the initial momentum? The particle is initially at rest, so initial velocity is 0. That means initial momentum is 0. And how do we write P final? It's mass times final velocity. And the mass is 1.4 kilograms. So we have 1.4 times final velocity equals 24. And we solve it for V final. Okay, so this is an example of how we use area under the graph as an impulse of the force. And we also combine it with impulse momentum theorem to find the final velocity. Here's another example how impulse can be used. In the collision tests or crash tests, 90 kilonewtons can cause a bone fracture, and acceleration up to 150 gravity accelerations within 4 milliseconds, or 50 times the gravity acceleration over 60 milliseconds will cause a fatal outcome or fatality about 50% of the time. Within such collision, we can calculate whole body impact pressure. If it's greater than 3 times 4 to 10 to the 5 times 10 to the 5, it's also gonna lead to a lethal 50% outcome. So that is equivalent to force of 90 kilonewtons. We're going to consider a typical collision that involves a 75 kilogram passenger and the car is going from 27 meters per second to a full stop. So the final velocity is 0. We're gonna write down our impulse momentum theorem and say that the impulse that this person received equals to change of its momentum. And then solve for the average force acting on that person. After we substitute all the numbers, including that the final momentum is 0 and the time interval is 0.01 seconds or 10 milliseconds, we're getting that the force is going to be around 2 times 10 to the 5 newtons, or 200,000 newtons. This is equivalent within this time interval to an acceleration of 200 accelerations of gravity, 280 g. So if we want to calculate the whole body pressure, which is roughly half a meter squared, we take our force, average force that we found from the change in momentum or impulse, and divide by this area. We are getting 400,000 newtons per meter squared, or 400,000 Pascal. And we know that the fatal limit is 340,000 newtons per meter squared. So this speed is definitely very dangerous. This is a graph of force on a car versus time in a typical collision, and similar calculations for different time interval of 0.15 seconds give us that the whole body pressure is 270,000 newtons per meter squared. So this there are seat belts and airbags in the car, and these are the safety measures that reduce our average acceleration to only 18 g, because it reduces the total time of the person coming to stop. Remember, it was 10 milliseconds and now it's 150 milliseconds. So these measures reduce everything by an order of magnitude. Okay, now we come to momentum of a system, parts of which interact with each other. So here are the examples of two bodies that each have its own individual momentum, and they undergo an internal interaction within the system. So we know that two objects that are in direct contact with each other experience third Newton's law action and reaction pair of forces, or the force that first object applies on the second equals to the force of that the second applies on the first, but opposite in direction. Also, if a proton is in the vicinity of helium-4 nucleus, which we call an alpha particle, they interact through Coulomb's reflection. In this case, because opposites, similar charges repel each other, and because of that, they can affect each other's momentum. But their individual momentum can change. However, we'll see that the total momentum of two particles does not change. Same as in case A, even though these forces will change the momentum of M1 or M2, but the total momentum of these two will not change. So, as we said, the two forces between two particles are equal and opposite of each other. However, if the interaction lasts for time interval delta t, the change of momentum for the first object will be equal to impulse of the force that the second object applies on the first. And the same is for the second object. The change of momentum of the second object equals to the impulse of the force that's acting on it, which is the force from 1 to 2. So before the collision, the particles have equal and opposite velocities, and after the collision, they'll have different velocities. But as we will see, the total momentum of the system will remain the same. This type of system that only experiences internal forces, we're going to call an isolated system. So here's the graphic representation of these impulses from 1 to 2 and from 2 to 1. And because of the forces due to, according to third Newton's law, are equal and opposite, the impulses within the same time interval are also equal and opposite. But then we recall that impulse equals change in momentum, so we can say the change in momentum for both particles is equal and opposite in direction. That means mass 1 times final velocity of 1 subtracted mass 1 times initial velocity of 1 is negative of the same, which is the change in momentum for mass 2. M2v2 final minus M2v2 initial. Then we are going to rearrange. We're going to put initial momentum on one side and final momentum on the other side, and we will see that mass times m1 times v1 initial plus m2 v2 initial, which is total momentum of the system initial, equals m1 v1 final plus m2 v2 final, which is total momentum of the system final. So these three or four equations, actually 5, are proving momentum of conservation of the momentum of the system that is isolated, or it only experiences internal forces between the parts of the system. Another application of impulse and momentum theorem is or momentum conservation is that a person that jumps up is using a force that is changing the momentum of the person. It might seem that the person that's jumping upwards from rest might appear to violate the conservation of momentum because his initial momentum is 0, and after the jumping, he's acquired a momentum from somewhere. But we need to consider that in the case of person that's jumping, just the person is not the whole system. That person is only part of the system of person plus Earth. So since the person is getting some momentum upwards, it means he received an impulse from Earth pointing upwards. However, as we have seen, that means Earth received an impulse from the person pointing downwards. But why does Earth not move? It's because the mass of Earth is much bigger, so the velocity of Earth as a result of such interaction is much smaller. So let's now do think pair shared 2, talking about a boy that's standing on the floating raft in water. So there's a water and there's a raft in the water, and there's a boy that's standing on one end of this raft. So if this is the shore and the boy starts walking, I'm sorry, if the shore is here and the boy starts walking away from the shore, as the problem says, towards the opposite end of the raft, what will happen to the raft? Will it stay where it is? Will it also move away from the shore? Or it will move towards the shore? Let's give you a second. So the answer is that the raft at the same time will move towards the shore. Because if the boy gains a momentum, initially when everything was at rest, the total momentum of the system was 0. As the boy is moving in one direction, his momentum is not 0 anymore. That means that in order to maintain the total momentum 0, the other part of the system of boy and raft needs to get momentum in the opposite direction. Or we can say that the boy receives an impulse and it gives the same impulse back to the raft. The same impulse, but opposite in direction. So that's why the raft will move towards the shore. Okay, now we're going to stop for a while, and then we will record second part of the lecture.